There we go. So welcome back to Origin Seminar. Today's speaker is Galen Bergsten. He's a graduate student of Ilaria Pascucci, of Ilaria can call it, in LPL at University of Arizona. So here we go. Take the floor, please.
Great. So greetings, everyone online. My name is Galen, and today I'd like to talk about some work that I've done as part of the AlienX team in collaboration with many members, including Ilaria Pascucci, Hai Smulders, Rachel Fernandez, and Tommy Koskinen. We're looking at exoplanets on the population level. So asking how groups or subsets of planets might behave based on their distributions overall. So the title of this talk is both sort of a pun and a punchline. The pun is that I will be talking about long and short period planets. But the punchline, to make a long story short, is that our understanding of planets at long orbital periods is highly contingent on our interpretation of planets at short orbital periods. I hope that's an enticing enough teaser, so now we can get into some of the science. I'd like to begin by talking about the Kepler mission. Kepler is, of course, an orbital space telescope designed to use the transit method to detect, in part, Earth-like planets in the habitable zones of sun-like stars. And to do this, it was focused at the Cygnus constellation, where there just happened to be a large amount of sun-like stars. But after a while, Kepler broke, so it started spinning around the sky, looking at exoplanets throughout the galaxy in what's known as the K2 mission. For today, I just want to focus on Kepler's primary field, so looking at this one patch of sky. And while Kepler was staring there, it found some 3,000 odd confirmed exoplanets, which is great because it really opened the door for the first time where we had enough numbers to actually start doing population statistics, where we could start looking at distributions of planets, how they behave both as a function of their size and also the distance from their star, or here their orbital period. You can start to see some of those distributions pop up already. There are places where there are a lot of planets and some where there are maybe not too many. And I'll draw your attention towards the bottom right, where there is a noticeable lack of Earth-sized planets at an orbital period of 1 Earth year, or the conventional habitable zone. This is maybe because these planets are rare, but more likely because they are just really hard to find with Kepler. And this is frustrating from an astrobiology perspective, because it means that we can't answer a lot of questions when looking for the next Earth, like how common Earth really is, or where we might find the next planet like us that can host life. Nonetheless, many people have estimates for how common these planets actually are, which is something we'll move into in the latter half of this talk. But for the first half, I'd like to address your attention to the place where there are a lot of exoplanet detections, which is here, the close-in population, or planets with orbital periods of less than 100 days. There are quite a lot of them, partly because they are just easier to find with Kepler, but also because there are simply more of them. So as a result, there are a lot of cool distributions that people can start to study when looking at the close-in population. And as any exoplanet demographics talk is obligated to tell you about, I have to bring up the planet radius value. Turns out there's this weird quirk of the close-in population, where if you plot the frequency of planets as a function of their size, it's a very strong bimodal distribution. There appear to be a lot of planets a little bit larger than Earth, or these super Earths, and an abundance of planets just a little bit smaller, or these smaller than Neptune, or these sub-Neptunes. But there's a noticeable lack of planets between the two, and this is the so-called radius valley. Now, there are many ideas for how the radius valley has come about and why we see it in the distribution of planets today. But the framework I'd like to work on for this talk is that it's an evolutionary feature, that planets do form in and around this radius valley regime, but they get pushed out of this and clear out this area into the super Earth population because they're shrinking. As for how you actually shrink a planet, the simplest way is to just remove some of its atmosphere. So I'll start with this cartoon of some sub-Neptune-sized planet, and it has a considerable atmospheric envelope around it. And this planet is orbiting pretty close to its star, so that makes things very hot and it's highly irradiated. Things are hot enough that some of the atmosphere can start to leak away, such that after long enough times, we might be left with a planet that has lost all of its atmosphere, or this so-called remnant core. Now, this core is small compared to the original planet, small enough that you might now consider it to be a super Earth. The problem is that this planet, while being the same size as planets that started as super Earths, certainly followed a different formation and evolutionary pathway to get to where it is today. Yet with Kepler, they're too far away for us to follow up with good masses, so we don't know what they're like compositionally. And we can't really do super great detailed atmospheric characterization, so all we can do is take this super Earth-sized planet and put it in the super Earth-sized bin, even though it might not have formed that way in the first place. And this sort of begs the question of, okay, how do planets actually lose their atmospheres? And I'd like to highlight two of the leading models or mechanisms today. The first is the idea of photoevaporation, that a planet which is very close to its star receives a lot of radiation, in particular XUV radiation, spoilers, and specifically XUV or X-ray and extreme ultraviolet is really, really good at ionizing some of the lighter, more tenuous layers of the planet's upper atmosphere. So you can get this outflow as a planet receives a lot of irradiation over time, and that can cause you to lose a large amount of your atmospheric envelope. The second idea is core-powered mass loss, which is much more focused on the planet and the planet interior itself, where you have this core underneath all the atmosphere that is hot. It's hot enough that you can actually start to boil away some of the atmosphere from the inside. And the catch here is that partly the temperature of the planet depends on its equilibrium temperature, which is related to the volumetric luminosity that it gets from the star. So in this sense, both of these models are in some way dependent on the luminosity that they're receiving from their star, the flux. And that means that you might expect as planets move further away from their stars and they receive less flux, then perhaps the effects of atmospheric loss become weaker. And to illustrate this, I'll show you some occurrence rate plots, which are a pretty typical way to diagnose these two populations. So here I'm plotting as a function of orbital period, the Kepler completeness and reliability corrected occurrence rates. So how truly common these intrinsic populations are for super-Earths in green and sub-Neptunes in blue. You'll notice that they behave slightly differently. At very short orbital periods, you have maybe an order of magnitude more super-Earths than you do sub-Neptunes. But as you move further and further away from your star, the sub-Neptunes start to close that gap until at longer orbital periods, they are as common, if not more common, than super-Earths. So this suggests some underlying behavior and interconnection between these two populations that might cause their distributions to be shaped differently as we see them today in the relatively old Kepler population. To give you one idea, I'll start off with this cartoon population of exoplanets as they've initially formed. And I have a group of sub-Neptunes here in blue and some super-Earths in green. And this white box is denoting my super-Earth-sized things. Now, the planets at very short orbital periods are highly irradiated, they're hot, so they're prime contenders to lose a lot of their atmospheres, such that after maybe a few billion years of evolution, the population could look something like this, where now at short orbital periods, I've removed the atmospheres from some of my sub-Neptunes. And that causes these remnant cores to now fall into the super-Earth-sized bin. But as I mentioned, these planets are distinct from the true intrinsic and underlying population of primordial super-Earth-sized planets. They could be compositionally different, but they've certainly followed a different evolutionary pathway to get to where they are now. And you can already start to see it here, but I'm showing that the effects of atmospheric loss are falling off with period. As we get further and further away from our star, these planets are receiving less flux, they're cooler. So you can strip less of your sub-Neptune atmospheres, which means that you're converting less of your sub-Neptunes into super-Earths, which is to say that if the population of super-Earth-sized planets consists at least partially of these remnant cores from former sub-Neptunes, then as you move further and further away from your star, the relative amount of super-Earths should start to decrease. Sticking with this cartoon framework, I'll now throw up this plot which is looking at the fraction of my small planets that are going into the super-Earth bin in green and the sub-Neptune bin in blue. At all orbital periods for my initial population, 2 out of my 5 planets are super-Earths, so my fraction is always 40%. But in my evolved population, at short periods, things have gotten twisted. At short periods, some of my sub-Neptunes have fallen into the super-Earth bin, so now I might have 4 out of 5 planets, which are super-Earth-sized, so that fraction is closer to 80%. Again, some of those sub-Neptunes don't belong there, but we don't have an easy observational way to tell that they're these remnant cores. They're just super-Earth-sized objects as far as we can tell. But as you move further and further away and the effects of atmospheric loss start to fall off, then less of your sub-Neptunes are converted to super-Earths, so that fraction gets untwisted. And you start to recover this ratio that looks much more similar to the primordial or intrinsic population. Now, this is, of course, just a cartoon and purely theoretical, but it sets up the framework for us to consider this idea of fractions with real Kepler data. So I'll return once more to these true occurrence plots. And now I'll consider how much of my occurrence, my small planet occurrence, comes from super-Earths in green, sub-Neptunes in blue. You can also think of this as the relative overabundance of one population or the And the point where these two lines are equal is where super-Earths and sub-Neptunes are present in equal abundance. So again, you'll notice some period-dependent behavior. In short periods, much of our small planet population is coming from these super-Earth-sized planets, which could be indicative of atmospheric loss, that here we're creating a lot of super-Earth-sized things because we're stripping some of our sub-Neptunes. As you move further and further away, that process becomes weaker and weaker. Eventually, you reach this long period population where atmospheric loss might be a little bit less efficient. You are converting less of your larger planets into smaller planets. Now, when I talked about the effects of atmospheric loss, I mentioned that one depends on XUV luminosity and one depends on bolometric luminosity. So both of these are luminosity dependent, and there's a pretty well-known relation that a heavier star is a brighter star, at least for the main sequence, sun-like stars that we're considering here. So you might expect that a heavier and thus brighter star can put out more flux with which to strip a planet's atmosphere. So you can strip more of your population out to further orbital periods. So under this same fractional framework, let's now consider how those trends might behave in different stellar mass bins. Here is what we found. Each of these 5 panels is a different bin of stellar mass, going from your lightest K-type stars in the top center to your heaviest F-type stars in the bottom right. You can see the same general trend in all of these, which is great and also not unexpected. This just suggests that all of these populations could evolve under the same mechanisms of atmospheric loss. But what's really interesting is how these trends might behave differently as you move from one bin to another. So these sort of neon solid curves that you can see are some model that we fit to this trend. And this vertical black line is telling us where those two curves intersect. So where we go from having a lot of super-Earths to having a lot of mini-Neptunes or sub-Neptunes. You'll notice that that black line moves further and further out as you get to heavier and heavier stars. So for your lightest K-type stars, it's closer to maybe 8.5 days. But as you move towards your heaviest F-type stars, then it pushes out to around 25 days. This is just another way of saying that perhaps atmospheric loss is stripping more of your planets to further orbital periods around heavier stars where you have more flux. To give you another way to visualize this, I'll now plot that best fit period as a function of stellar mass. That looks like a pretty strong relationship to me. This solid orange line is showing approximately how those periods scale with stellar mass. And they do so like roughly stellar mass to the 1.7th power. Now, that number is sort of interesting because it provides us with a baseline that we can then compare to predictions of photoevaporation or the core powered mass loss models. I'll return once more to this comparison and note that as XUV and bolometric luminosities both scale with stellar mass, they do so a little bit differently. So it might be interesting to consider how these two relevant luminosities scale with stellar mass. But considering that the effects of atmospheric loss are cumulative, then it also makes sense to consider how the time integrated or cumulative luminosity and mass relation evolves. So here, I'll start with looking at XUV luminosity using some evolutionary tracks from the work of John Stone et al. From 2021. And on the left are a set of luminosity mass relations, and each of these curves represents a different set of stellar ages. So at the bottom are stars that are roughly only 10 million years old. But then as you move further and further up to the top to darker and darker colors, you're integrating that luminosity for longer and longer until you reach here the relevant age of the Kepler field, the median age being approximately 4.6 billion years old. You might notice these sort of gray dashed lines, which are indicating some log-log fits to the mass luminosity relation at each time step. And the exponent of that relation, so luminosity proportional to stellar mass to some power, that power is then plotted on the right as a function of time. So you can see how the luminosity mass relation evolves as we get closer and closer to the age of the Kepler field. You'll notice that when you start out pretty young, that relation is maybe a little bit shallower, and as you get older and older, it moves closer and closer to being about stellar mass to the roughly squared power. We can look at the same thing for core-powered mass loss, where bolometric luminosity is now relevant. So here I'm using some tracks from Barat et al. 2015. So we do a very similar thing, and you can find that core-powered mass loss, the mass luminosity relation sort of levels off much more quickly, such that by the time you hit the Kepler field, your exponent is more like stellar mass to the roughly 4th, maybe 4.5th power.
Like, what are the error bars on in the right-hand plot?
On the right-hand plot, these are just the error bars on the exponent of like a log-log fit from luminosity proportional to stellar mass.
So it's just on the fit to that
Yeah. This is just sort of like a back of the napkin comparison, because now we have these luminosity mass relationships, which aren't quite the same as these period mass relationships I presented earlier. So we can do a quick conversion by stepping through flux space. And what you might find is that for XUV luminosity, the relevant scaling could be period proportional to stellar mass to the roughly first power. But core powered mass loss is much steeper, more like stellar mass to the roughly 2.8 power. Those numbers might sound a little odd to you, because if we return to this plot showing the scaling that we observe in the Kepler field, I'll point out that the scaling we observe is more like to the 1.7th power. So this is actually a little bit steeper than what XUV luminosities and photoevaporation would predict, yet also a little bit more shallow than what core-powered mass loss and volumetric luminosities would predict. So here we have some observational result that is approximately intermediary between these two models and mechanisms of atmospheric loss. Now, there are plenty of considerations you could make to bump these numbers one way or the other, which aren't super easy to do in an analytical fashion. So one of the things that I'd like to do in the future is some numerical modeling of population synthesis, where we consider maybe some end-to-end models, observing how this trend evolves with both stellar mass and time to see if we can't recreate what we observe in the modern Kepler field. But for now, this is sort of a teaser that there could be something more nuanced happening with this atmospheric loss mechanism. So to recap everything I just said in the first half of this talk, we introduced this idea of a fractional occurrence, where you look at how many of your small planets go into the super Earth bin or the sub-Neptune bin as a function of period. And it's reminiscent of a population that might have evolved under the effects of atmospheric loss. We also find some scaling with stellar mass, which is useful in comparing and constraining what the dominant models and mechanisms might be, but it's currently somewhere in between what all the theories predict. So there's a little bit more follow-up work to do on this front. With that, let's take stock and go back to the title of this talk, where I told you that we would talk about both long and short period planets. But so far, we've only talked about short period planets, the close-in population within 100 days. And I put this lovely buzzword of the habitable zone in here. So now let's shift gears a little bit and start talking about the populations we might expect to find at longer orbital periods. I'll return once more to the Kepler population and again highlight this frustrating lack of reliable exoplanet detections for Earth-sized planets in the habitable zone. Yet I mentioned that there are plenty of estimates for how common those planets actually are, so I figured it would be useful to give sort of a background on how some of these estimates come about. And the easiest thing to do is to look at the population where you have a lot of detections, like the close-in population, and then fit some model that describes how that occurrence behaves as a function of period. Now, this is just a cartoon of a broken power law, which is the typical form that people adopt. Here's a plot from Vespucci et al. 2019, which is showing a very similar thing to the occurrence of these small close-in planets. And we'll come back to this plot in a few moments. So once you have this model that describes how the close-in population behaves with period, then you might extrapolate it to longer periods like the habitable zone. And once you're there, you could integrate over the range that you're interested in both period and radius, and that would give you some estimate for eta Earth, the formal notation for the occurrence rate frequency of Earth-sized planets in the habitable zone. Now, of course, everyone's definitions of how wide the habitable zone is or how wide Earth-sized means, it's all different from paper to paper. So one thing we can do to make comparisons a little easier is to introduce this metric of gamma Earth, which is the only equation I will show you for the rest of the talk. And this is basically just like a formality to normalize over your integration range. You take your actual habitable zone occurrence and divide it by how wide you said the habitable zone was in period and also in radius. So gamma Earth is a really useful comparison because it lets us confront different models to see what numbers people are coming up with. And here is just a host of some of the recent literature values. You'll see that they are occupying a large swath of parameter space that all of these different works are entertaining. And I should mention that these are only the works after 2018 that are using the final data release of the Kepler sample. And these numbers are all over the place, but I might set a useful baseline towards you. Highlight this number towards the bottom, Kepler et al. 2018, which, as I've plotted here, is the occurrence rate that was used and estimated the mission yields for both LUVOIR and HABEX that went into the recent Astro 2020 decadal. I'll also point out some of these more recent results by Steve Bryson, Michelle Kunimoto, and company, which are adding this new statistical metric of reliability, which is a good way to value astrophysical false positives and statistical false alarms. So it just makes your Kepler planet sample a little bit more robust. I'll also highlight this outlier here by John Zink and company, which is considering the effects of multiplicity. Say that you have multiple planets in a system. Kepler has some weird quirks where it's good at detecting the first one in that system, and then as you detect more and more, maybe it gets worse and worse. So this is a really interesting consideration and another thing that you can do to try and unpack what the actual occurrence of habitable zone planets is. Now, a lot of these are using this extrapolation method from the close-in population out to the habitable zone. And in doing so, you sort of make the implicit assumption that, first of all, nothing really drastic happens in between those two in your occurrence distributions, but also that your distributions for the close-in population are a good fit for the types of planets you would expect to find at habitable zone periods. But that might not be true if, for example, the close-in population was shaped by some process that didn't affect planets at the habitable zone. And in the context of this talk, that might start to raise some red flags. I'll return to this metric of fractional occurrence, where we were looking at just the close-in population, but already starting to find some evidence that atmospheric loss has a period dependence. It's very, very effective at shaping planets on the left side of that vertical black line. But as you start to move further and further away, then that process starts to look a little bit weaker, and you start to produce less super-Earth-sized planets. This might be a problem if you're basing your estimations on the close-in population, but you have a process that is period dependent, but not accounting for that period dependent behavior. To give you an example of this, I'll jump back to 2019 in this paper by Piscucci et al. Here's the plot I showed you previously of some fit to an exoplanet population, which is including planets down to about 2 Earth days orbital period. Now, 2 Earth days is sort of an interesting number because this is always on the left side of that black line from earlier. This is always in the regime where atmospheric loss is making a large amount of these super Earth-sized planets. So you could expect to find a high number of super Earth-sized things at very short orbital periods, but you wouldn't expect to find those at longer periods when atmospheric loss has become inefficient. On the right is a set of models fit to a similar population, but now excluding planets below about 12 days. So here you're making a cut to exclude a lot of those remnant cores produced by atmospheric loss. Now, if these blue and black lines are denoting the best fit occurrence as a function of period, you'll notice that on the left, in the case where you include those remnant cores, by the time you get out to the habitable zone, you have a much higher occurrence rate than the one on the right. So why is this? Well, on the left, you're presuming that you make a lot of stripped cores at pretty much all orbital periods. So that causes you to sort of overestimate the actual occurrence of small planets at longer periods where you aren't making them because atmospheric loss isn't really a big deal. To illustrate that again graphically, maybe the population of planets looks something like this in orange, where at long periods you don't have a lot of these remnant cores. But if you assume that you make them at a lot of orbital periods, you can end up with a distribution that is much higher in the habitable zone because you are now overestimating the occurrence of Earth-sized planets. So I'll return once more to this metric of fractional occurrence and highlight a very interesting proposition that has now arisen by our adopted parameterization for this model. Here, we are definitely fitting to the close-in population down to 2 Earth days, where atmospheric loss is a big deal. But our model has these 2 separate regimes separated by this black line. On the left, we have a population where atmospheric loss is creating a large amount of super Earths. And on the right, we have a population where that regime has sort of fallen off. Now we have not a lot of super Earths where atmospheric loss isn't really a big deal. So if atmospheric loss isn't affecting the habitable zone, then you might expect this longer period component to be a little bit more reflective of the planets you would expect to find in the habitable zone, where atmospheric loss, again, isn't an active process. Now, there's a catch, which is that the plots I'm showing you here are asking how much of your small planets go into the super Earth bin or the sub-Neptune bin, but they're not actually telling you how many small planets you have. So there's this second component of the model, which I've glossed over until now, which is just governing the overall period distribution of small planets using this very typical broken power. So we can take our model and fit it directly to the Kepler population, and then ask how many small planets we expect to have at a given orbital period. And once there, we can ask at that period, how many of those small planets go into the super Earth box for the sub-Neptune box. Again, it's this longer period component that is presumably a bit more reflective of those you would expect to find at the habitable zone. So once we have this, we can extrapolate our model in both period and down in radius to ask what the occurrence of Earth-sized planets in the habitable zone is. And before I do that, I'll again remind you about the values that everyone else has come up with. I'll highlight once more that this result from Bryson and Co. recently is considering the reliability of these planets. This result from John Zink and Company is considering multiplicity. And then I'll highlight this result from Pascucci et al., which is this model where they've excluded stripped cores. So presumably this is the first model to directly account for atmospheric loss, but here they just make sort of a hard cut on the population they consider. Now I'll tease that our work is using this consideration of reliability, so we're vetting for these weird statistical false positives and astrophysical false alarms. We're also doing a more direct consideration for the effects of atmospheric loss. Choicely, we're not considering multiplicity, partly because we're splitting things up as a function of stellar mass, and it becomes really, really hard to consider that when you're dividing your sample on sort of a mass basis. So we consider two of these numbers, and I'll show you what we find, and be the first one to tell you that these numbers are kind of small. There are several reasons for why they're small, and I think they're important to consider, especially in comparison to everyone else. First of all, we've split things up as a function of stellar mass, whereas the previous works are considering usually some conglomerate of F, G, and K type stars together. So by splitting your sample, you'll necessarily decrease the amount of planets that you have in each of those bins. But furthermore, we can also directly incorporate any dependencies on stellar mass. For instance, the fact that heavier stars tend to have less small planets. That ends up being reflected in our occurrence rates here. But perhaps the biggest source of this difference is our direct consideration for atmospheric loss. Here, we are presumably not overestimating the occurrence of Earth and super-Earth-sized planets in the habitable zone. So, to summarize how we got to these numbers, the close-in population is shaped by the effects of atmospheric loss, but the habitable zone population probably isn't. And once you account for that difference, the occurrence rates that you are likely to find are on average much smaller, because you don't overestimate the presence of Earth-sized planets at long orbital periods. So great, those numbers are small, but why should you care, and what does this actually mean? Well, I figured I could contextualize some of the implications for these results in the context of something that has set the exoplanet world ablaze recently, which is of course the results of the Astro 2020 Decadal Survey. We got this formal recommendation for a 6-ish meter class life-finding telescope. And 6 meters is sort of a funny number because it's actually not dissimilar to the design of LUVOIR B, as many of them would love to tell you. LUVOIR has this inscribed diameter that is actually comparable to about 6.7 meters. So a lot of people are using the statistics for that mission as sort of the baseline for what you might expect from this decadal recommendation over the next couple decades. Now, one of the big catches with the HabEx and LUVOIR concept studies was that the occurrence rates they adopted to predict their yields were presumed independent of stellar mass. Yet I've shown you some evidence that perhaps that is not the case and that these values are very much mass dependent. So now it starts to become an interesting exercise to consider what types of stars and planet systems this mission could be biased towards. As an imaging mission, it is necessarily limited by its inner working angle or how close you can get to the star for something to still remain resolvable. So I figured it would be fun to plot the habitable zones for some different stars in terms of their inner working angles as a function of distance from the telescope to the star. So this blue band is representing the habitable zone for some of your lighter K-type stars. Orange is your sun-like stars, and F-types are here in green. Now this horizontal black line is showing the LUVOIR B inner working angle, suggesting that anything that falls below this line is no longer resolvable. You'll notice that by the time you hit about 14.5 parsecs, most of the habitable zone for K-type stars has become largely undetectable. There's sort of a catch that, well, the habitable zone for F-type stars technically remains large enough separations that you can resolve it. Those planets are now so far away that they could be very low contrast, so they're actually just hard to see. So maybe there's some sort of sweet spot for solar mass stars that are a little bit larger that this mission would be really good at finding planets in them. But if we jump back to our recurrence rates and then highlight this number at the bottom, which is the results that we used in designing this mission here, an occurrence rate of around 24%, you'll notice that our numbers are much smaller than previous estimates and what these missions were built upon, suggesting that perhaps for sun-like stars, the mission yields could be lower by maybe a factor of 5. Now, as much as I love doom scrolling, I get enough of it from Twitter every morning. So instead, I'll leave you with this important message that understanding what's different about these occurrence rates is really, really important as we move forward to design this mission. There are tons of different considerations that all of these works are considering, and here we only include just a few of them. So there's still room to improve, and still a number of factors that we can consider as these models go forward and this mission comes to fruition. So I'm happy to start taking questions here. If you're interested in future details, you can check out our paper, which is currently about to be resubmitted. But in the meantime, I would be elated to take any questions.
Any question?
You can go first.
So in the first part of your work, you only fit the period where you have the equal occurrence for the super Earth and sub-Neptunes. But in that panel plots, there are much more information other than just the period. So do you have any plan to use other information in that?
Sure do. Maybe I'll just jump around. So we can take a look at some of these models and highlight a few of the details that I glossed over, like the fact that there are, well, this black vertical line is being fit as a free parameter. There's also a bunch of other free parameters, like we're fitting the value of this plateau at short periods, the value of this plateau at longer periods, and also like the curvature between them. So there are more free parameters than just the one that are constraining this. So that there are lots of things governing the overall period distribution. In case you're interested about, for example, fitting the radius distribution, you can also make the radius value a free parameter and we'll find something very similar.
Okay.
So I think my question is actually related to this. So you find this transition where the occurrence rates overlap basically between sub-Neptunes and super-Earth. So I was wondering, first, how do you define what's a super-Earth and what's a sub-Neptune? Do you, for each of these stellar mass bins, search for the bottom of the valley, or how do you do that?
Yeah, so it's a little bit simpler than that. For example, here these are the completeness weighted period and radius distributions for each of our stellar mass bins. And you can see there's this abundance of super-Earths and this abundance of sub-Neptunes. And so there's this work from 2019 by Wu, which is considering, suggests that the stellar mass radius value scaling goes like stellar mass to the 1/4 power. So we adopt that same scaling and then sort of position where this local underdensity is in each of these stellar mass bins. So the radius value moves around as a function of stellar mass.
So, but the position of the transition, of course, depends on the relative occurrences and how they behave. So are you worried that there is any underlying bias that maybe super-Earth are harder to detect and there was a systematic error in determining the biases when they came up with the occurrence rates? Yeah,
so first of all, these are fit directly to the Kepler data, not the occurrence rates. But it is also considering the completeness and reliability of each of those planet candidates. So presumably it corrects for the biases. But as for the positioning of the radius value, while this is the one I'm showing here, and these are the results that are in this paper and presentation, you can just position this however you want. You can normalize it differently. You can implement some other scalings. We've tried all of it, and the results are very robust to that. So the punchline is that it is a much more extreme dependence than anything you can implement here.
Cool, thank you.
And this is I had another question, but I think you just answered, but I had another comment, which I think maybe we talked about a couple of months back, is that Maximo and I have a paper where we calculated the change in the occurrence rates if you just look at single stars, which bumps things up. So, I mean, if you still have a chance to point that out, I think, in this work, if you're trying to prevent people from thinking that you're trying to kill habitability studies, right? It does help, and it'll help especially those larger the higher mass numbers where the multiplicity is higher. So that calculation we didn't differentiate between K and F stars, but that does move the numbers back up a little closer to what
I didn't shout it out here, but it's also in the paper.
Okay, so you calculated that, so it does. So people think that there's some hope if you do your survey, but I mean it's the same idea of just doing the survey design carefully. It's so important.
Okay.
I was curious, the plot you were just on with your fractional occurrence rates, can you just say what's going on with the very last period bin with the uptick in the super Earths?
Yeah, so you'll notice that these small colored numbers at the bottom are the number of planet detections in that bin. So here we're talking about single number statistics. So while the behavior could have that uptick, it also could not. Either are consistent to 1 sigma. Largely, we're presuming that this is likely an effect of small number statistics. Thanks.
Rachel.
I'm on this paper, but I still have questions. If you go back to slide 8, thank you for putting in slide numbers.
I got it.
So you're saying that's your starting model, right? The initial population. Why are you assuming that there are more mini Neptunes than super Earths when we don't know anything about the initial conditions, and that's something we're trying to find out?
Yeah, so this longer period component that we're fitting in the model is presumably the population that is not shaped by atmospheric loss. So it might shed some information on the distribution of planets before atmospheric loss happens. Of course, that's maybe better explored by looking at, for example, young clusters with tests where you can look at these planets before they've lost a lot of their atmospheres. But there's also this interesting work by Sandoval et al. Back in 2020, which is considering here, this is like the ratio of super Earths to sub-Neptunes as a function of time. So at really young times, that ratio is somewhat small. So perhaps they are more comparable, but as you get older and older, then you start to add more, you start to take sub-Neptunes and turn them into super Earths, so that ratio starts to go up. But largely, that cartoon is just sort of to introduce the framework. And then the fits to the model itself don't assume that sub-Neptunes have to be more common than super Earths, but that's what they find.
So you're kind of taking beyond that, the transition line, you're assuming it's intrinsic. That's the intrinsic population because they're unaffected by the most common evolution models.
Yeah.
And then you're interpolating that for I guess that's the word.
Yeah, I guess like a time-dependent.
Okay.
Yeah. Yeah, that's the interpretation.
Okay.
Or one of the interpretations.
Any other question from online audience? Yeah, I have one, just maybe clarification question. There was your comparison of Habitable Zones occurrence rate of your work and other works. So what the mass range or is basically the same for the other papers?
With the mass?
The mass, yeah, because you had 5 points.
Yeah.
Yeah, but the other ones, there were basically ones. I guess that's the average of different mass. But the range of the mass, are they all kind of for different references, literature? Are they kind of similar?
Yeah, so most of the papers that I referenced there are considering, the ensemble of FG and K-type stars, but the definition of like what is the top of the Fs and what is the bottom of the Ks
Right,
might be a
exactly.
little different. For the most part, a lot of people are using the classic Mamajek table.
Okay.
So the catch is that a lot of people have previously been doing things as a function of stellar temperature, whereas this time we're some of the first to do it as a function of stellar mass. And there's some overlap on the edges.
But not vastly. Okay, thank you. Right,
I think you had a question.
Oh, we have a question over here, all right? Oh, okay, Daniel.
Oh, thanks. Yeah, very nice talk, Galen. So I think these are very important results. I had one question. So you mentioned different contributions or different inner working angles for the habitable zone for different spectral type stars. Did you actually do any estimate for what would be the contribution in terms of host stars for the planets that would be detectable, given a volume or a given inner working angle? So just looking at the numbers or what you showed without the actual occurrence rates of the stars, I would guess that this is mostly K dwarfs that you will be be providing the directly imageable, basically habitable zone or size planets.
Yeah, presumably. So yeah, I've sort of in the background of this also been looking at the catalog of nearby stars within maybe 30 or so parsecs. And it's starting to shape up that a lot of them just happen to be K-type stars.
Okay.
It's nearby. It could be really interesting, and I think many members of AlienX are already working on this, which is estimating what the actual distributions could be in the solar neighborhood. So,
Do you know how much is for example, the inner radius of the habitable zone is changing for K dwarfs. I mean, for M dwarfs, they go on, the habitable zone moves around. And so I'm wondering what, that's less of an issue for G dwarfs, but I'm wondering for K dwarfs, especially if most of the planets do come from the late K dwarfs, whether a fraction of them actually have spent time in interior of the habitable zone. So that may permanently change their habitability potential.
Yeah, I haven't looked into the time dependence. This is assuming the relevant luminosities for current age of the Kepler field, like 4.6 billion years old. But I think you could do some interesting work with seeing how these wiggle around with time and what biases you might have.
Mm-hmm. Okay, thanks.
Okay, two more questions. First, Yasuhiro's question is written in the chat. Nice talk. Question about slide number 12. If the inner disk edge is truncated by stellar magnetic fields, how would the results be affected? You can go to chat.
Yeah, just truncated by stellar magnetic fields.
Yeah.
Interesting. Yeah, I don't think this is something we've considered. It's perhaps a little bit more primordial or at earlier times than the framework that I've set up here, where you just have some planet population at different periods. It could be very interesting to study, and I would need more knowledge of disks to do it, which I don't have. There are definitely some knowledgeable people that I could ask about it.
Yeah, I think it is very important to follow the chat. Right, I think Andrew has a question.
Yeah, this is a question about the backup slide you were just showing with the stellar ages. Yeah. So it's curious. Obviously, there's a model in here, but I gather it's also data. I'm just sort of curious. My understanding was that obviously ages of stars are quite difficult to determine. So how?
Yeah, they sure are. This work I gave a talk on like 2 years ago and don't remember it in super great detail, but I believe they are using the ages from the Travis Berger 2020 catalog, but only using the subsample that is informed by spectroscopic metallicities. So that's only like a third of the Kepler field, so like 60,000 stars, but presumably pretty good ages. There's obviously some room for error, and here they do like an MC model to constrain some of the uncertainties on ages, but you'll notice that 2 of these models are just like flat bars because they don't have enough information. So there's room to improve on this for sure.
Thanks.
Age is super difficult.
Very hard.
All right, any other questions?
I think there might be one more in the chat.
One more in the chat. It says, Yasuhiro says thanks.
Oh.
Yeah. Okay, otherwise, let's thank Galen again. See you next week for the last talk for this semester.